Hello, hello. And for today's Fiddler, I have a circle here in orange. And for the purposes of this problem, I'm going to call it a unit circle, so with radius 1. And I am going to want to cover this circle with two ellipses. And I want those ellipses, they have to be congruent, meaning they're the same size and shape. You can rotate them and move them around, but they have to be the exact same size. And I want to take these two ellipses, completely cover the circle. I want the ellipses to be as small as possible. That's the problem. How small can I make these ellipses? So when I first started thinking about the problem, I thought we were going to end up with something like this, where the ellipses kind of crossed each other, going in different directions. And I was going to see how small I could make that. But it turns out this is pretty wildly inefficient. And just to take you on the journey that I went through, um, there's actually a fairly well-known result that was stated in the Fiddler problem about circles here. So, and to think about that problem, that gave me the insight for how to actually think about um, the correct solution here, or at least what I think is the correct solution. So, so the well-known result is that if I have a circle and instead of two ellipses, I'm going to cover it with two circles. How small can those circles be? And it turns out that the smallest they could possibly be is the exact same size as the original circle. So why is that? Well, if you take the two circles and you make the purple circle any smaller than the orange one, you're going to have little bits sticking out that you can't quite cover. And you can slide them around. It doesn't really matter. You're never going to cover the whole thing. And the intuition for why this is true is that if I think about just one of those circles and the perimeter on the bigger circle that it will cover, it's always going to cover less than half of that perimeter. So with two circles, I'm never going to be able to cover the entire perimeter, no matter how I place the circles. And so there's always going to be some part of the bigger circle sticking out. So with that in mind, I thought, well, now with the ellipses, all I need to do is cover half the perimeter and then make the ellipse as small as possible. And that it does work. I think that's probably as small as you can get it. I don't know that for sure. I don't have a good proof. But that intuitively is at least, I think, fairly reasonable. And so if I think about this circle, I'm going to center the circle at the origin. So these intersection points are going to be, 1, 0, 0, 1, negative 1, 0. And then I want to think how small can I make these ellipses? And I'm orienting it this way to make the math a little simpler. You could do it arbitrarily, but it gets quite complicated. So the basic formula for an ellipse is x squared over some constant a squared plus y squared over some constant b squared is 1. Now this assumes two things. It assumes that your ellipse is centered at the origin and that there's no skew, meaning that the kind of oblong shape of the direction of the ellipse is either parallel to the x or y axis. Now in our case, that's not quite true, right? It is true that the way I've set it up, it is parallel to the x-axis, but it's not centered at the origin. So to correct for that, I'm going to include another kind of variable, capital Y, which is going to be my y offset. And now I'm going to stick that in there, and this is going to be the equation for the ellipse that we want to figure out. So what we want to figure out is essentially the values of a, b, and capital Y that will minimize the area of the ellipse, but still touch those 3 points. So my assumption here, and I think it's fairly trivial to see that in the two-dimensional case, in the 2-point case, in the two ellipse case, in the case we're talking about now, that the ellipse is going to exactly touch all those points. And so I can use those points as equations here. Now, unfortunately, two of them are essentially the same, but that's okay. So if I use the point 1, 0, y is 0, x is 1, so it's actually 0, 1, then I can figure out that b is 1 minus y. And then if I go ahead and plug in either 1, 0 or negative 1, 0, I get another equation, which will give me a in terms of y as well. But, you can do a couple of steps here. You can plug what I already solved b for, and then I can get a in terms of just y. Now, because I only have two equations and three unknowns, then I need to use the minimization fact here. So, sorry, not two equations. I have 2 points essentially, like two distinct points to plug into this equation with three unknowns, which I guess is essentially two equations. So I'm going to use the area for an ellipse, which is just pi times a times b, where a and b are the constants from the equation of the ellipse. And doing that, I just plug in for a and b, and I get this kind of messy, this 2 here is a squared. It's not a square root symbol here. And I want to minimize this in terms of y. Now you could go ahead and take your derivative, but you're actually going to you're going to find that there are two roots between 0 and 1 here. And so if you do it that way, you'll then have to take the second derivative and figure out which one is the minimum, although I think it's fairly intuitive which one's going to be the minimum, which one's going to be the maximum. But you could do it that way. Honestly, I just plugged this into Wolfram Alpha because I couldn't be bothered to do the chain rule and the product rule that would be required. But if you think that's fun, feel free to do that. You should end up getting capital Y as the third in this minimization. Now, it seems like because it's just such a nice number that there should be some intuitive reason for this. Maybe it's just my poor ellipse, my geometry understanding of ellipses. I can't see the intuition for why the offset has to be a third. If you do, please let me know. I'd be interested to hear that. If you plug that in, you'll get an area of about 0.77 pi, which is less than 1. So by using ellipses instead of circles, we have improved the area somewhat, as we kind of should have expected, I think. So that's the main question. And I guess you could double this to get the total area of all the ellipses that you have. Now, what if instead of 2, I have 3? Well, I'm going to have the same logic, but now I'm going to only take up a third of the perimeter instead of half the perimeter. So here, if I take a third of the perimeter, then the relative points here, now I'm orienting it this way so that the ellipse maintains that property that it's oblong kind of in the direction of the x-axis, but you could do it any way you want. Again, it'd be messier, but you could do it. And if you remember your trigonometry, if I do a third, you could set up some 30, 60, 90 triangles and see that the points here oriented this way are going to be positive and negative root 3 over 2 in the x direction and 1/2 in the y direction. And I also need to make sure that I touch the top here with this ellipse. And but that's not quite enough, actually. So if I just have those 3 points, I could draw an ellipse here, but 3 of those are not going to cover the entire circle. So to make sure I cover the entire circle this way, what I want to do is add a 4th point, which is the origin of the circle. And I'm going to say that the best I can do here is to stretch this ellipse a little bit so that it also touches the origin. Now, I'm actually not, I'm definitely not 100% confident that this is correct here. There are a couple things I could see going wrong. The first thing that I can see going wrong is that this is the less likely thing that I think would be wrong here, is that I could see it might be possible to not touch all 4 points here and minimize the area if you could, stretch it a little bit and make it less oblong in some way and kind of shave off some excess area somewhere else. I could see that possibly working. And it doesn't make intuitive sense to me, but if someone, showed me that that worked, I wouldn't be like, no, that's definitely wrong. So that's one way that this might go wrong. The other way this might go wrong is I could imagine some way that you could tilt these a little bit so that they don't all have to hit the origin, right? One can get a little bit of the origin, the other ones can be offset a little bit to not do it. I don't think that is going to work, but again, if you found out a way that does work, I wouldn't say, oh no, there's no way that would work. And I don't have a good proof for, why it has to be exactly this way. But this is my intuition for how it should work. And, we'll see on Friday if it's right or not. So the math here is actually a bit easier because I have 4 points now and, 3 distinct points really in terms of the equation. And they're distinct because I have this offset y here. And so what I can do here is I have, one of the points, 0, 1 is exactly the same as before. I get the same setup for b. But now because I have the origin as well, I also get that b is not just 1 minus y, but it's also y, which tells me that y has to be a half. And that, again, is very intuitive to me, right? If I go back to this picture, if I stretch this purple ellipse down to the origin, it's fairly clear to me that the center is going to be at 1/2. So then I can plug in the either of the right or left points here, and I'll get 3/4 over a squared. And then because I have y as a half, that very nicely corresponds to the 1/2 in my y coordinate, and so those will cancel out and be left with 0. And so I'm just left with 1 is equal to 3/4 over a squared, and which of course gives you a is 2 over root 3. So now I can just plug these in. I have b, which is 1 minus y, which is 1/2. And I have a, which is 2 over root 3. I can just plug that in very easily and get area is about 0.58 pi, which again is less than when I have 2. But if I triple it, that's more than if I double the area of the ellipse, the minimum ellipse with 2. So my thought is, as you get bigger, the total area might increase. Bigger meaning the number of ellipses you use. Although, at some point, this logic is going to break, right? So at some point, it's definitely not going to be the case that if you had 100 ellipses, you certainly aren't going to be stretching all of them from the perimeter to the origin. I don't know where that breakpoint is. I think that'd be an interesting problem to maybe solve computationally, but I'm not going to do it. So hopefully someone else did it, and Zach can tell us about it. So anyway, that's my thought for where this problem should go. If you have any other insights or thoughts here, especially if you understand intuitively where that 1/3 comes from, please let me know. All right, thanks for watching, and I'll see you again next week.